Hello and welcome back. So far we have seen most of the kinds of robotic sensors which are used in the industry. We have seen optical encoder, we have seen position sensors of various other kinds. We have seen how to convert a position sensor signal to a velocity sense signal, how an accelerometer is made, and Hall effect sensor in general, how it can be used for various purposes. We have seen force sensors. So with these most of the kinds of sensors which are there in the industry, so let us just discuss how these sensors are classified, how the property of each sensor is mentioned in their technical data sheet, what are major factors with which you can compare different sensors. So that is what we will be covering today. So let us begin. So yes, this is one leftover portion of our syllabus, but yes, this is quite simple as well. So what is this? You must have seen it quite number of times at various places. So these are known as limit switches. What this roller is basically doing, this particular item is mounted using these bolts over here, and they are fixed to the mounting, and this lever can move like this. Okay, so what is this? This is nothing but a limit switch. Okay, switch as rightly told. So it can be normally open type. Normally open means a switch is normally open. If you press it, it is closed. So there are many other switches which are normally closed type, so if you just press it, it will become open. Apart from that, there are many other types in which it can be double pole type, in which you have just one single lever has got two different wires which are cut. Okay, so that is how it can directly switch on two wires at a time. Okay, or it can make two wires at a time. So yes, these are different ways. So it looks like this. A number of places includes this may be included at the printer, in your printer, a 3D printer. This is nothing but a pedal switch. Probably you have seen it on a sewing machine. Sometimes they are not just switch, they are gradual switch. That is not a switch as such. It can be a potentiometer. This type of levers are quite common. These are like joystick, and it is there in earth moving vehicles with commonly. So yes, these are a few of its kind. Yes, if you remember, your fridge also has such switch. Okay, so as soon as you lock your door, shut your door, your light goes off. Right? In your car, maybe when you open your door, your light switch is on. So yes, that also has this type of switch. Okay. So yes, let us just see how sensors are classified. So yes, we have covered sensors. Sensors are internal sensors, external sensors. So internal sensors basically gives you the state of a machine. Okay. So this can be position, it can be velocity, it can be acceleration, and acceleration sensor can be used like a force sensor or otherwise also. So yes, these are four major kinds which gives you states, and then position sensor can be of linear and rotary. Linear sensors and rotary sensors both can be of incremental, absolute. Yes, potentiometer, it used to do our job. Apart from incremental optical that you have seen, it can be a potentiometer. Linear variable differential transformer, we didn't go through this. Resolver, you have seen, it is a AC sensor, AC signal sensor. Okay, so velocity sensor can be of multiple kind. It can be of position sensor, tachometer, Hall effect sensor you see. Okay, and acceleration sensor can, any force sensor can be used like an acceleration sensor as we saw in our module. And MEMS, micro electromechanical sensors that you have seen. Okay, force sensor, this in detail you know now, can also be a Hall effect switches or a piezoelectric switches which can also be used like this. So yes, these are some of the internal sensor. External sensor gives you the state of an object, how your machine is encountering the environment. Okay, so what is the status of this table, maybe when it is marked at the corner of this room. So if it is aligned, so there may be some switches which gives you exactly the state. When it is perfectly aligned, both the switches should be 1. Okay, both the switches should be on. So these are few ways these are used. So this is limit switch. It can be a pneumatic switch, it can be piezoelectric switch, it can be pressure transducer which can be used like this. So all these are external switches which gives you a state of the environment. Okay. So proximity switch is there, that is a similar kind, but it gives you proximity without having any contact with the environment. So those were, let's say, we have discussed about at least capacitance sensor or inductive sensor, right? We have also seen Hall effect sensor. Microwave sensor is also there, but we haven't gone through that in detail. Ultrasonic sensor, laser sensors are there which are very precise, and vision sensor which uses machine vision to do its job. So yes, broadly we have gone through most of these types of sensor as we have discussed in different lectures of this module, that is sensors. So yes, now let us move ahead how to indicate the performance of such sensor. Okay, how these sensors, when you go and check their data sheet, what all parameters which are there that specify that particular sensor. Okay, so one of the very important parameter is the range. Okay, let's say you want to inflate your simple balloon or type of tire which is there in your car. So yes, in order to do that, for cars it can be 0 to 35 bars would be quite good enough. Okay, sometimes they have different specific unit depending on the tradition which is being followed, and sometimes they are SI system. So definitely unit is one of them, that also will specify the type of reading which is graduated on the dial, or if it is an electronic sensor, the output may be linearized based on the unit also. Okay, so yes, that is the range which can tell you. Okay, so that is there. And then error. Error is, let's say, this pneumatic pressure line is of 6 bar, but it is showing you 6.5 bar all the time. So that is the desired one is what actually it is, and the actual one what your sensor is showing you, what your sensor is showing. So desired minus actual is the error signal. Mostly your data sheet shows error can be plus minus 1% of the full scale reading. That means if it is 100 bar, so it can tell you, let's say 99, or it can tell you 101 bar. Okay, but that is the maximum error which they have found through experiments. Okay, accuracy is the extent to which a measured value might be wrong. So how much is the maximum error which is possible? Okay, so extent to which the value might be wrong. Okay, so wrong is this, that is the error. Whatever is wrong, it comes under this. Okay, so that is there. And sensitivity is the your device sensitivity is not always desirable. If it is an oversensitive, it becomes very difficult to measure something. Okay, so just like your let's say weighing machine which is there. So you just put in one small weight on top of it, it immediately starts fluctuating. It goes very high and then overshoots, it comes back. So they may be very sensitive to even a small amount of weight. It becomes very difficult to just see the actual value which it should give. So it is naturally sometimes damped to make it happen, or sometimes, so it is the output versus the input. Okay, so input is the signal which is coming, and output is the actual value that it should show. So depending on the value, how they are calibrated. So yes, it is sometimes digitally controlled, or sometimes it is a property of your system in case of mechanical sensors. Okay, so non-linearity is something which is again not desirable, because it becomes very difficult to estimate the kind of signal which is there. Okay, let's say if it is a displacement sensor which is coming out of a potentiometer, you know it is linear. Okay, so output voltage is proportional to your input displacement. So if it is 0 to 180 degree for 0 to 5 volt, so if it is showing 2.5 volt, you can directly say yes, it is 50% of what is the full scale thing. Okay, so that is how linearity helps you in estimating the value, understanding the value which is coming out of it. Otherwise, if it is non-linear, it is very difficult predicting that, very difficult programming that. You have to have a complete set of table, lookup table kind of thing in order to understand the actual parameter which you are measuring. Okay, so yes, also parameter which is known as hysteresis. So while loading, it has, let's say you have a spring balance, with an indicator which is on this. So if you keep on increasing the weight, it comes here exactly when you were going from 0 to 10 kg, let's say. So 0 to 10 kg, it came exactly here while increasing the load. When you started with 0 kg and then went on to 10 kgs, so it came here for the 5 kg load. So while going back also, it should come exactly to this place, right? So it should show while unloading, it should follow the same pattern and go back. But normally that is not the case with some old type of sensors in which this is not taken care of. So yes, it follows a line which is something like this. So while loading, maybe it is follows this. So unloading, it follows a different curve and come back. So for 0 it is 0, for 10 it is 10, but for 5 it may not be 5. Got it? So there are different way in which hysteresis or behavior can be explained. So one of them is Smith-Trigger behavior. In this line is almost like this, which is rectangular. Okay. Another one is a rubber band kind of behavior. Okay. So it is a curved shape while going up and curved shape while coming down. So 0 to 10 is something like this. So anything which is 5 will be somewhere over here. So you got the idea basically what it is. So it is very, very undesirable thing, and normally they are very well compensated to not to see this kind of behavior in your sensor. Okay. So yes, another very important parameter is repeatability. It is ability to give the same output for repeated application of the same input. For the same input, again I'll give you a very good example like a potentiometer. So potentiometer is my favorite example. So for the same input, that means for same position, if it is total scale is 100 mm, you are at 50 mm, so it gives you 2.5 volt. Every time it is at 50 mm, it should give you 2.5 volt as an output. So it is highly repeatable. Okay, but yes, over the time, you know, this particular slider gets weared off. Okay, so it goes bad due to dust on top of it, maybe moisture. In that case, this will not be the case. So it is not repeatable if it is accounted, if the value is accounted for over a period of time, things have gone bad. So yes, that definitely doesn't come under the purview of repeatability definition. So in case of repeatability, for at the same period of time, means maybe on the same day, you multiple times you have measured and you got a different output. So basically, if this should be the output and you are getting signals somewhere over here, okay. So what is repeatability? Repeatability is defined as the smallest circle which should contain all the data for a given value. So that is how a repeatability is defined. We have discussed this also while we were discussing our robots repeatability, that is the actuator repeatability we saw. So it is exactly in a similar way. Most of the terminologies which are here also applies for your robot, so, or maybe for an actuator also. So most of them. So over here we are concerned mostly about sensors. Quite a few of them also applies for actuators or even for a complete robot, at least for repeatability now you know. Okay, so next one is stability. It is the ability to give same output for a constant input over a period of time. So if it is giving you a constant output, it should remain there. Okay, as long as input is not changing, output should also not change. Okay, that also should remain constant. But what happens sometimes due to change in temperature, output varies even when input is not varying. So that is known as a drift. So it can be due to the temperature, that is one of the major cause of this, or sometimes due to the material deformation which is happening. So if it is a beam on which you have applied a strain gauge sensor somewhere over here, it is giving you in terms of voltage. So this voltage for the same load may change with time. This voltage may change with time. So that is because of maybe a creep deformation of this beam if it is for a longer duration. So that is one of the cause. So there are many other causes which causes this. So that is what is stability should remain there. Okay, so dead band is a range of inputs for which there is no change in output. It is very clearly explained by backlash which is there in mechanical gears. If one of them is a driving one, other one is the driven gear. Okay, so what happens, there is some clearance. If this is driving this, the clearance is on this side. So when this starts rotating in opposite direction, this will pick up, but after a lag of, after a period of time. So this will start, this will take at least this much amount of time before it establishes contact. The driven shaft is not going to move. So that delay is there. So that is the dead band, when your output is not changing even though your input has changed. So that is a dead band. That also is there in few sensors. Okay. So mostly in case of amplifier, you may have some dead band where a small, very small change in the input, your output is not responding only. Okay. So it is sometimes given as your amplifier picks up after a period of time. So that is the dead band which is there. So yes, and then you have a resolution. It is the smallest change in input that will produce an observable change in the output. Okay. So again, your device may be having an analog to digital converter. Okay. So that has further resolved your voltage to further digital values. Let's say if it is 1024 number of graduations you have in your dial, which gives you as an output in case of optical encoder. So you cannot see any displacement if it is less than 360 by 1024 angle. So for that much small angle, it is not giving you any pulse. If it goes beyond that, definitely it will give you one high pulse. Okay, so that is the idle time. Within that, it is not going to give you any change. And all the changes that you see are in slots. Okay, all the slots will give you output in this fashion, and this is the least amount of distance that you can measure, at least angular distance in case of optical encoder. So that is what is your resolution. Okay, and then you have output impedance. Normally for electrical devices, electrical sensors, output impedance is very important, because connecting this sensor to your input device, maybe a PC, maybe a DAC, should not change the behavior of this sensor. Okay, so that is why this impedance is very, very important. Okay, so actually when you connect it to this, actually the total resistance of this device changes. Okay, because it becomes something like a parallel resistance which is there. Okay, so effective voltage across that changes. So connecting this device changes the property of this. Let's say it is giving you in 0 to 5 volt full scale. When it is connected, it gives you 0 to 4.98 full scale value. Okay, so that impedance matters here. So normally it is very, very important in case of electrical output. A bandwidth is the maximum operating frequency, how fast your device can change. Okay, that again is very, very important. At least you have seen such case in case of proximity sensor. Proximity sensor, if it goes beyond 20 kilohertz, off and on, it is behaving as if it is completely, totally on all the time. So instead of giving you off and on, so it is giving you uniform, constantly on signal. Okay, so it is giving you this. So beyond certain frequency, it gives you bad results. Okay, it is not getting switched off properly. It is not. So there are devices with different frequency which is to be selected well before implementing in your application. Okay, output type can be many. So in case of potentiometer, it was voltage. Okay, sometimes they are giving you output as a current, or it can be mechanical output in case of optical encoder. However, the output was optics, but yes, it was later on converted to an electrical signal. So it can be optical fiber which is used to transmit long distance data. So in that case, your output is in optics, which later on requires a digital to analog converter, or maybe optical to electrical converter. So yes, again the level output of a potentiometer, you can find an analogy to it. So if it is maximum full scale value is 0 to 5 volt in case of embedded system, so it can be 0 to 24 volt in case of industrial electrical system. So yes, this is pressure. Pressure can be another type of signal which is commonly used in case of pneumatic sensor. Okay, at least in case of nozzle flapper that I see. Okay, that we have not covered, but yes, you should now understand different output what it can be. Okay, and then environmental condition, that is also specified in the data sheet. Working temperature, although it is a pressure sensor, but you should be remain within this band of temperature so as to get the precise or claimed value which is there by the manufacturer. Standard temperature and pressure, so that is mentioned in this. Okay. Yeah, apart from this, it can be ingress protection also, maybe. Okay, so it has to work in that particular kind of environment where dust and water molecules should not go beyond this size. Okay, so other things are like size and weight. Okay, sometimes they are very, very important. I'll give you an example. When in earlier days we used to have gyroscope, so gyroscopes were very, very big. Okay, those were something around 5 to 6 kg or maybe 12 kg in load. Nowadays with MEMS sensor it can be in few milligrams. Okay, so that is the difference. So 5 kg to this almost like a 0 kg now. So you have huge lot of difference with technology. So that 5 kg additional ammunition that our aircrafts can nowadays carry. So that is one of the very good example when weight of these sensors do matter. If it is your wristwatch or maybe a mobile device, so sensors, you see there are plenty of sensors. Each one of them accounts for certain weight. Okay, so if those are very, very big, so it is very difficult to manage your mobile phone on your pocket. Got it? So yes, reliability is another thing. So yes, it is very much related to many other properties like your system parameters. They do vary with time, or they do vary with the environmental condition. If it goes bad even by a small amount of time, it goes bad. So I'll show you with at least for a force sensor, it is ready to take up, even if it is designed to take up a load up to 100 Newton, but when robot collides, it can go up to maybe 1000 Newton. Okay, but if that force sensor is able to take up that load at least for a second, you are done. Okay, your device will not go bad. Those are very expensive sensors. So at least for a small period of time you can overshoot, but normal range is okay 100 Newton. So you got my point. So that is there. So that is the reliability of such thing. Maintainability, let's say in case of standard load cell, so it needs calibration every 1 year. Okay, so that is maintainability. Every 1 year you have to go for test, which is to get its calibration done, so that it gives you a similar value as it was when it was new. Okay, then the cost. Yes, sometimes force torque sensor, at least which we normally use in robots, they are hugely expensive. Even for a very small scale, sometimes 100 Newton or 200 Newton capacity, they are very, very expensive. Okay, so yes, that cost, they do matter, at least for our research, and not for at least for defense, but at least for research or maybe for medical application. That cost, they do count a lot, because it is ordinary people who are paying for it. Okay, now we'll look at static and dynamic characteristics of a sensor. So yes, why this is so important? Because as soon as your sensor gets the signal, it doesn't give you an output which is exactly what was desired. So it takes some time to stabilize before it gives you an actual output, or maybe very near to an output. Okay, so this is a dynamic behavior of a sensor, which is very, very important. So how much time, what are different parameters which are important in order to deal with such behavior of your system. So the one which we discussed so far were static characteristics of a sensor. So those doesn't change with the type of input or behavior in the input kind. So they remain the same, but yes, your output, let's say if it is in terms of voltage, based on the dynamic inputs, okay, so that output is not that the way it should be. So how it is, actually it behaves something like this. Okay, let us say your sensor should show this value somewhere over here, like it is 10 Newton over here, which is input to your sensor, your force sensor. So what happens, your device immediately starts sensing the value, and it takes certain amount of time actually to start also. So it took at least this much of time to begin, then it started rising up, your output started going up, it overshooted a bit, and it came down and it stabilized to the actual value which is there. So it took at least this much of time to come to that value. So that is the problem with this type of sensor, or any sensor to say, because they have a lot of components which are there inside. Sometimes at least in case of optical sensor, at least in case of inductive or a capacitive proximity sensor, you saw there are components. Okay, you had a oscillator circuit, you have a pickup circuit which used to pick up, and then ADC, then digital converter, then communication device. So there is a latency sometimes, or there are internal system behavior due to electronic systems which are there, that is something like a spring mass damper system. Okay, so it takes some time, it goes overshoots and it comes back, it gives you a good value. This time should be very, very small. If it is to work with robots, it should work in a real time. Got it? So this curve explains it all. So how your device is. This curve is normally not there in most of the data sheet, but they will specify some parameter, specific parameter, which is related to this curve. So what are they? Let us discuss that. So first parameter which is there was your response time. It is expressed as a percentage of input. So what is the response time you see here? So this is your response time, you see. It is marked in this. It is marked here, you see. This from value from here to here is the response time. After that your device actually started moving, actually started going up. Okay, so hope you got this. Okay, so mark till here, this is the time it took to start giving you some value at least. Initially it was giving you a 0 value, later on it picked up and it gave you some value. Okay, so now let us move ahead to other parameters. So next one is time constant. Time constant is expressed as 63.21% of response time. Actually, it is very much related to kind of you have studied in radioactivity half-life or something like that. So this fractional value comes very much similar to a value 1 minus 1 by E. It is given by 1 minus 1 by E. So this is the factor. Okay, so this is given as 0.6213, 6312. So in percent it is equal to 63.21%. So this is what is a time constant. This much percent of your response time, and then you have a rise time. Rise time is the actually specified as a percentage of steady state. So if it has to come up to this state, okay, so normally it should reach till here. Okay, so this is the time from here to here. Okay, so this point in your space, basically this is the point, and you have this point. So it took at least this small gap of time to actually come up to a real value, which is actually input to this device. Okay, so this is the rise time, amount of time which it takes to reach to that, at least to 95% of the actual value. So that is your rise time. Okay, then comes your next parameter, that is the settling time. So how it is expressed as output settles within some percentage of steady state. Almost just 2% is remaining, so almost it is steady. Okay, so that is what is your steady state time. Okay, so that is where it has almost settled. Okay, so it is specified somewhere in this region. So that is the region where it has almost real to the near to the actual value which was input from your environment. So that is what this sensor is also showing. So there is not more than 2% to 5% of deviation at that region. So the amount of time, this is your settling time. Okay, so now let us see few of these if it is there in the technical data sheet of few of these sensors. So now I'll move on to some data sheet, physical data sheet of few sensors. Okay, so this is one of the sensor which is typical rotary encoder, optical encoder. Okay, so see what all parameters which are given here. So this is ordering information. This is there. Basically, they are the type of nomenclature this company may be using. So it belongs to 291 series, termination of kind of V1. V1 means so many pins of some pin size is given. So these are some of the more detailed explanation which is here. Bushing length, shaft length, what is the length of this shaft which is here. Shaft is trimmed with a kind, so it can have just a slot, it can be C cut. Okay, so different cuts which are here, so it can be slotted, it can be flat cut. Operating voltage can be different. So yes, switching kind, class, Smith trigger. So these parameters are specifically given. Okay, so this is one, so available with different kind of pulses. So 64 pulses per revolution. This is a small optical encoder. Okay, it may be useful for some small kind of stuff, but yes, it is there. So other parameters are, you see, voltage is 32 pulse per revolution. Okay, voltage maximum is 64 pulse per revolution. Output is 2-bit quadrature in form channel A and channel B. Okay, two channels are there. Sync current is 5 volt, power consumption 5 volt, of something around 80 to 150 milliwatts. Resolution of different kinds it supports. There are many other parameters which are here. One of them is IP rating. So if it is of 32 ppr, max best possible is IP 50, but for 64 ppr kind it is IP 40, which is below to that. Anti-static tray packing is there. Packing is very, very important. Sometimes these sensors are picked up by some robots in electronic assembly industry. So in that case, that packing tray size is also very, very important. So if this is a raw material for those kind of PCB manufacturing or device manufacturing company, so that is very, very important. This is the operating temperature, environmental condition it is giving. Storage temperature is different, working temperature is different. Right? For different PPR it is different, pulse per revolution. So different kind of sensor, it is same range. Rational life. So you see these many parameters which are there. Okay, so physical dimensions are given. Okay, so this is another kind of incremental rotary encoder, but this is a very special kind. That is the reason I showed you today. So it can give you 1024 to 2048 signals for a period of 360 degree, but it also gives you a incremental encoder with sine cosine interface. That means it is just like a resolver also. It can behave like a resolver. Okay, so this is external parameters. So pulse count is fine. Okay, then there are many other parameters. Operating voltage, you see, it is just 5 volt. So if at all you are interfacing this sensor to any industrial interface card, so that should have a dedicated output for 5 volt. You cannot feed in 24 volt here. Output is sine and cosine signal. Okay, apart from that, so there must be some configuration software or kind of thing which can change the output type. Sometimes they do have some kind of switch which is there, which can change the type of signal that it gives. Okay, so there are various certifications, you see. standard conformity certifications which are there. Okay, so here is your output. So you see two phases are there, A and A bar, B and B bar. One of them is sine A, other one is cosine. Okay, so difference voltage will let you know the exact position of your shaft. That is one way of doing it. This is an ATI 4-stalk sensor. Let me just, there are many parameters which data sheet can give. Very important one is the electrical parameter. So that is here. Okay. So you see it can measure something around 0 to 150 Newton. Okay, along different axes. This is a 6 degrees of freedom. So torque along all the axes X, Y, Z is this. Fz is this. Along Z axis it has more value, whereas in X and Y axis it can take up less force. Okay, and there must be some default peak values. So if it is a regular kind of force which it is measuring, that is fine, but how much is the peak that is encountered while it is encountering any sort of accident or those things. So this is your peak values which are there. So yes, so this is a cylindrical proximity sensor. You see different models are there, they depend on sizes basically. M12 size, that is the size of the kind of thread which is here, with which it can be mounted to one of the panel maybe. So yes, M18 or M30. So these are standard size. Sensing distance varies, 4 mm, 8 mm, 15 mm. So all of them are of 3-wire kind, can be a PNP or it can be NPN type. So 3-wire basically. Output is just 1, 2 of them are supply. So 0 and maybe 24 volt, and output is in the range of, because it is digital in nature, it is 0 or 24 volt or 0 or 5 volt, it depends on type of device it is given. Okay, so differential travel is there, sensing distance is there, set distance is this for this device, 0 to 5.6 mm. So you cannot, there is no setting screw or somewhere, you have to change the device altogether. So maximum distance that it allows is something around 10 mm. It can detect, you see, conductors, that is metallic conductors, and it can also be any sort of dielectric which changes the dielectric of the environment nearby. So this may be a non-metal also. Okay, so leakage voltage, there are many other parameters also. This is for a accelerometer ADXL 345. So you see it can go up to 16 G of external acceleration. Okay, so let us just see the functional block diagram. It is exactly similar, the one which I discussed in the class also. So this is there. So let us directly go to the parameter sensor input. So input can be this 2G, 4G, plus minus 8G, plus minus 16G. So it can be used as a collision sensor also. Non-linearity is there. So it is expressed as a percentage of full scale. So maximum will be 0.5% of non-linearity. That is the error that you can see. Misalignment error is there. So cross sensitivity is there. So different range. So this is your resolution, 10 bit of resolution. That means 0 to full scale. Let us say it can go up to 2G of measurement, maximum 2G. So smallest part of G that you can see is 2G by 2 to the power 10. So that is the least value that it can give you, it can show you as an output. Okay, so that is the 10 bit, that means 2 to the power 10. Sensitivity is here, you see, that is there. So even smaller, so what is, how it is expressed per G, it is least significant bit that is going to change. Offset is there, that is, it should not be there, normally you don't expect it. So noise level, that is also given here. Specific operating voltage range 0 to 2.5 volt. Operating temperature range is also there, minus 42 plus 80. Device weight, this is very important if it has to go on top of any mobile device also. ODR is given, you see output data rate, it is 100 Hertz. Okay. So Your output data is in this is the maximum sampling frequency with which you can get the data. Okay, so that is there. Supply current is mentioned. So you see, these are some parameters. So let us. Okay, so that's all for this module, that is sensor. So these are few of the references that I have given you. One of them is Introduction to Robotics. It's a robotics book, but it has a very good chapter on sensors, so that you can go through. One very important book, that is Sensors by W. Bolton. It's a mechatronics book. This will give you an insight to different sensors along with the electrical devices, along with the electrical circuitry which are there in few of them. So this is very good book, and at least test books, these are a few. Apart from this, you should go through the data sheet, you should go through the manuals, standards and certifications, types of interfaces, different types, IP classes and different safeties you should go through. So that's all for this module. We'll start with robotics after this. We are now ready with almost all the prerequisite for robotics. So we now are familiar with actuators. We know different kinds of robot, its classification. We have already gone through actuators, how to move a robot. So you are ready with all the gadgets now. So now you should start making robot. So from next module, we'll start doing that. That's all. Thanks a lot.